Okay, so from here you can see that the result, this is what? The image of open ball at center at x and radius epsilon, this contained in SRS Tx, that is the open ball with center at Tx and radius epsilon. If T is continuous, but no, T is contraction. This is true if T is a contraction, as we have seen right now. So, the answer is your C. Now, next is which of the following is false? Okay, any continuous mapping from the closed interval 0, 1 into itself has a unique fixed point. Okay, this is true because there is a result which says that every continuous function defined on a closed interval to itself has a fixed point. So, here this statement is true. The second statement is that any homeomorphism from the closed open interval into itself has a fixed point. No, this is not true. Okay, no, this is homeomorphism. Okay. So, here is any homeomorphism from the closed interval into itself. Okay, so this has a fixed point. The second one is any bounded continuous map from this into itself. This has a fixed point. Yeah, this is bounded. So, it must be, the image must be less than infinity. So, a bounded continuous function defined on this set has a fixed point. But any continuous function from the open interval 0, 1 into itself has a fixed point. No, this set should be closed and bounded. Okay, so here is this set is closed and bounded. So, this set should be closed and bounded. So, this statement is not true. So, these are some were some exercises, MCQs related to fixed point chapter, fixed point theory. Now, we will discuss some questions appeared in the NET exams during the last few years and related to the metric spaces. So, let us discuss some exercises. Okay, I have provided the answers of some questions, but not to all questions. So, okay, you can try by yourself, but we can discuss here. For example, this question is for any metric space, any metric spaces x dx and y dy. A map F from x to y is said to be closed. Whenever F is closed in x, then f of F is closed in y. Okay, so you know that the definition of a closed mapping, that is to say, image of closed set. Okay, image of closed set is closed, then we say that the map is closed, or you can say that the map is open if and only if the image of open set is open. So, for any subset B of a metric space, B is given the induced metric, that is B, okay, whatever is the metric of F, so on B we have the induced matrix, okay, that is the restriction of this on B. The metric x cross y, okay, the metric on x cross y is given by this dxy, x prime y prime is equal to maximum of the metric on x and the metric on y. Okay, the metric on x plus y is given in this way. Which of the following are true? Which of the following are true? Number 1, for any subset A of x, the inclusion map A, okay, that is to say, inclusion map A means I, okay, is a subset of A, Okay, so I of A is a subset of X. So if we take any subset, okay, if we take any subset of this, any closed subset of this, the image of this would be a closed image of this. Okay, so here is the second one is that because you have not the second one, the projection map from x cross y to y, it is given like this, projection of this on this one. So we have seen that every projection map is continuous. So every projection map is continuous. So this map is continuous. Now the question is whether this map is closed or not. Okay. So you have to check whether the projection map is closed or not. But it is continuous. This we have already proved. And f and g are continuous functions if the composition are continuous functions. Suppose that f and g are continuous functions. If the composition is closed, then the restriction of g on f of x is closed. Okay, the important thing is that the restriction of g, the important thing is that a continuous function, continuous means inverse image of closed set is closed. A function is continuous if on only if the inverse image of closed set is closed. But the image of closed set may not be closed. So, if function is continuous, it does not imply that the function is closed. Okay, but we have seen that if the composition map, okay, composition map is closed, okay, then what will happen? So you will have a situation like this. Suppose f is a map from x is a map from x to y, okay, and y is you have a map. So this is your f, and here you have z, and then the composition of this g composition f from x to z. Okay. Now here is suppose here you have f of capital X. So this is the map from this one. Now the question is these two maps are continuous, so they may not be closed clearly. Okay, so we cannot say, and the composition of closed set is closed. So we cannot say anything. You have to check. How we can check this? So the question is whether this set is closed. If this set is closed, this set is closed means you take any A is a subset of Z which is closed. Okay, then G composition F A is equal to G of F of A. This is closed. Okay, so this set is your closed set. Now, what are you getting? This set is closed set. Now we want to prove that if we are taking any subset here, okay, then this set, okay, suppose this is a subset. What is this? F of A. A is closed. Okay, so F of A may not be closed. Okay, so F of A may not be closed, and then how we can? But this whole is closed. So this is closed for all f of A, whether f of A is closed or not. But this would be a closed set because this is closed, this is closed, this is closed. Okay, so the whole, whatever is this one, whether this is closed or not. Suppose if this is closed, then f of A is closed. So because this set is closed, so this must be closed set. So this must be closed set. It means that whatever is this G of A, G of say for example y is closed. So if you take y is a subset of f of x, okay, then g of y is closed, and therefore this statement is true. So you can see that this statement is true. So this way you can prove that the statement is true or false. Okay, so this statement is true. Okay, now you take f is a map from x to y, takes closed balls into closed sets. Then f is closed. You take from closed balls to closed sets. Now keep in mind, every closed ball is a closed set. Okay? Every closed ball is a closed set. So it means that, but a closed set may not be a closed ball. So this statement is you have to check. Now we have the next MCQ. So next MCQ is, let P be a function defined from R square to R in the following way, that Pxy is equal to mod of x if x is not equal to 0, if x is equal, Pxy is equal to mod of y if x is equal to 0. Now the question is, my first question is whether P is a metric on R or not. Whether P is a metric on R or not. So let us see here is whether P is a metric or not. So Pxy is greater than 0, okay, because both for Pxy is equal to mod of x, Pxy is equal to mod of y. So Pxy is greater than or equal to 0, there is no problem. Now you have to check Pxy. If Pxy is equal to 0, then x must be equal to y. First, let us check. Suppose Pxy is equal to 0. So Pxy is equal to 0, then you can take Pxy is equal to 0. So this means that it is equal to mod of x if x is not equal to 0. Okay? If x is not equal to 0, then this cannot be equal to 0. From here, it is not equal to, if x is not equal to 0, if x is not equal to 0, then the Pxy is equal to mod of x. But x is not equal to 0. So this cannot be hold good. So this is not a metric space. This is, P is not a metric on R2. Keep in mind. So you have to, first question is okay. So P is not a metric on . Then the next question is, which of the following statements are true? So there may be several statements true. Okay. So this is, of course, the first statement does not hold good, as we have seen. But Pxy is greater than 0. Yes, this is true. This is true. Now what about this one? So if we take this one, then you can see that here you can take alpha, then alpha you can take mod of alpha from here, okay, mod of alpha, and from here you can take mod of alpha, and then from here we can take alpha is common, and then it is equal to Pxy. So this is true. But what about this one? So you have to check whether this is true or not. But just you can take the calculation, you put x plus y, here x1, y1, and here you can take x2, y2, and then you apply this one, you will see whether this is true or not. So this you can do by yourself, no problem. Then the next question is, consider a subset of R2 which is defined as a the x minus 1, x minus 2, y minus 2 and y plus 4, it is equal to 0. Which of the following? This is connected set, compact set, okay, and this is dense set. So which is true? So this you have to check. Okay, and then we have the next. We say that suppose that f is a continuous function. Okay, it is non-constant continuous function, and keep in mind here is the from close interval 0 1 cross close interval 0 1 to the open interval 0 1 to open interval 0 1, not the self map. Okay, and it is a continuous function but not a constant function. Then which of the following statement is not true? Image of f is uncountable. Okay, so image of f, so you can take a image of this set must be a subset of this one. So a subset of this is countable or not, this you have to see. Okay, so any subset of this set is countable or not. Okay, so you will get the answer. Path connected, you forgot about the compact set. About the compact set, there is a possibility that image of this set, because this set is continuous, but there is a possibility that the whole space, suppose if you take the whole space, then you get the open set. Okay, the image of the whole set is the open set. Okay, but here the function is continuous. So the image of this may not be a compact set because it is open, so it may not be compact. The image of f has non-empty interior, so this is also not true. Second is, next we have the following exercise. F be a continuous function from the closed interval. Which of the following statements are false? So they are same as the first exercise. So in the first one it was two-dimensional. Here is arc 0 cross 1, 0 1 cross 0 1, the closed interval, and here is both are open interval. And now you take a closed interval and open interval, and then in the same way you can check this one. Now I come to this one. The letter x is equal to set of all natural numbers including the plus minus infinity. And actually here you can say tau with the topology on x consisting u subsets u of x such that either u is a natural number or this is finite. So okay, let us take instead of taking tau topology, let us take tau is a metric on this one, such that u is an open subset of x, such that either u is a subset of n or u is a subset of the complement of u is finite. And let a is equal to n union plus infinity and b is equal to plus infinity. Then which of the following is true? So this you have to check. This is a very simple one, so I am not going to give this one. And here this is also involved the connectedness, so I am not going to this one. So let us take here is this one. Okay, let alpha is any when any real number alpha, let mod of alpha denote the greatest. So here is okay, it should be like this. Okay, this denotes the greatest integer smaller than or equal to alpha. Okay, greatest integer smaller than or equal to alpha. Define d as dxy is equal to the greatest integer function of mod of x minus y. So this is greatest integer function, keep in mind. Then which of the following are true? Dxy is equal to 0, but dxy is equal to 0. So whatever is dxy, if the difference, the greatest integer is less than 0, okay, if the distance between this and this is less than 0, you will get it is equal to 0. But in that case, x may not be equal to y. So this may not be true. Of course, this is true because if you take xy is equal to mod of x minus y, so you can write this as y minus x. So this is true. Okay. Similarly, you can see that because this, the mod of the function satisfies the triangular inequality, and therefore the triangular inequality holds good here also. Okay, so triangular inequality holds good. But D is a metric? No, it is not a metric because the first condition does not hold good, and so it is not a metric. And therefore, you can see that this is not a metric, and this is true. So 2 and 4 is the answer. Okay. Now take another MCQ. The next MCQ is that let X be a countable set. Then which of the following are true? There exists a metric D on X such that XD is complete. If D is countable, then you can also find a metric on X such that X with respect to that D is complete. It is true. There exists a metric D on X such that dxD is complete, is not complete. Yes, it is also true. You can also find there exists a metric D on X such that XD is compact. Yes, you can find it. You can also find. So there is a possibility that all are true. Okay, so you have to check 1 or 3 true or all are true. So check it. Now, X be a metric space in the original question. It is okay. So let X be a metric space. Let A1, A2 be two dense subsets of X, and E is a subset of X. Then which of the following is true? So E intersection A1 is dense in E. Okay. D1, A1 and A2 are dense in E. Okay, it means that the closure of A is equal to X, closure of A1 is equal to X, and closure of A2 is equal to X. So here is, you see that this is your A1 closure is equal to X and A2 closure is equal to X. And here you have E is a subset of this one. It means that E is a subset of the closure of A as well as closure of A, this one. Then the question is A intersection closure of A is dense in E. So if you take the intersection of this and this, then it may not be dense in E. Okay. The second one, E intersection A1 is dense in E if E is open. If E is open, then it may be denser, and E intersection A1 intersection A2 is dense in E if E is open. This may not be true. But E intersection A1 intersection A2 is dense in E if E, A1, A2 all are open. So this is true. So this you can check. Now take here is we have some exercise. Let CCR is set of all real valued continuous functions defined on R such that f is continuous and there exists a constant such that this is I don't know, so there is some problem, so we can left this question. So the next question is for any y in R, this denotes the greatest integer less than or equal to y. Define a function f from R to R by fxy is equal to x raised to the power mod of y. Then f is continuous on R2. So what you will get? You will get x raised to the power, always it is equal to, because the y is you always have whatever is your y. Okay, here you will get only the integers. Okay, so here you will get x raised to the power any integer. What you will get? It is a continuous function, except anything. So it is continuous function. So it is continuous on R. So what happened? It is 0, 0. So suppose it is equal to 0, 0. 0 raised to the power 0. So this is equal to infinity by infinity form. So here you will get, of course, except 0, 0. Because at 0, 0 this function you will get 0 raised to the power 0. So the rest is the function f is continuous. So here is the function is continuous. The f is continuous at no point of Rn. So you need to check. Now let us take X be a metric space and A be a subset of X. Then one can conclude that A is dense in X if X minus A is nowhere dense in X. Yes, this is true. A is dense in X, then the complement of A is nowhere dense set. If this is nowhere dense set, okay, this is nowhere dense set in X if A is dense in X. Yes, this is also true. A is dense in X if the interior of A is dense in X, complement of A is empty. No, this is not true. The interior of this is empty. Okay, if A is dense in X. Okay, A is dense in X. So when you take the complement of this, the closure of this, which is equal to your whole X. But this is not closed set. So this is not true. This is not true. Next is which of the following statements are true? Every compact metric space is separable. Yes, we have proved it is true. In a metric space, XD is separable, then the metric D is not the discrete metric space. Okay, can we say that a discrete metric space is separable or not? Separable means it has a countable dense set. So it is separable if and only if X is countable. Otherwise, it is not true. So every separable metric space is second countable. Okay, so check the results. So here you also, every first countable metric space is separable. Check for these the results which we have already mentioned. Similarly, here is this, we have mentioned that D1 is this kind of metric and you have D2 metric is this one. Then we have mentioned that if X is your natural numbers, then with respect to these matrices, whether X1, X2 are complete, totally bounded, not complete, this we have already done in our exercises. So you can do this. You can check the exercises which we have already done. F is a continuous function. Okay. And choose the correct statement. Every continuous function is bounded. The image of bounded set is bounded. Image of an open is an open subset, image of F is an open subset of R? Okay, the image of bounded set is bounded. So this is the image of bounded set is bounded. Okay, it means that this is bounded. So you have to check the results which we have already mentioned in this one. And also for this kind of the sequence, we have seen in the exercises whether this is continuous, convergent, pointwise convergent or not. And then, the hell, what is space? So we are not connected and this is connected. And these are the exercises. Here is again. So we can take this exercise. Let S is equal to set of all functions from R to R such that there exists epsilon is greater than 0, such that for every delta is greater than 0, mod of x minus epsilon is less than 0. F of x minus f of y is less than 0. Now keep in mind, what is the question? This is the set of all functions from R to R. Then for if there exists epsilon greater than 0. So here you can see that epsilon is greater than 0. Okay. So there exists epsilon is greater than 0 such that for all delta is greater than 0. This, okay, implies that this one. But this is not the definition of a continuous function. So this is not true. Okay. And of course, this is not true, and so this would also not true. If it is not continuous, it cannot be uniformly continuous. So this is also not true. The third one is it is bounded. Yes, you can say that whatever is x and y, but here you see that f of x minus f of y is less than epsilon. So whenever you choose any 2 point, this difference is less than epsilon. So the function is bounded. So here you can see that the f is bounded, but f is constant. This is not true. So only the true is that the function f is bounded. So answer is question number 3. Okay, then the next question is consider a set of rational numbers Q as a subspace with the usual metric. Suppose that A and B are rational numbers. Okay, A and B are rational numbers with A is less than B. And let K is equal to K intersection B close interval AB. It means that K is the set of all rational numbers in the closed interval AB. Okay, then K is bounded subset of Q. Yes, it is bounded because it is bounded by A and B. It is a closed subset of A and B, closed subset of Q. Okay, it is closed subset of Q in Q. Okay, it is a compact subset of Q? No. It is open subset of Q? No, you have to check all these things, whether this is true or not. But the first A is true. Because if B is all 1 is true and 2 is true, then 3 is true. Because it is closed and bounded subset of Q. So you have to check. Now if D and D prime be metric space, be matrices on a non-empty set X, then which of the following are matrices on X? The row 1 is equal to the sum of 2 matrices. Sum of 2 matrices is a matrix. The difference of 2 matrices may not be a matrix. The maximum of 2 matrices is matrix. The minimum of 2 matrices may not be a matrix. Okay, so the answer is 1 and the last one. Maximum is metric, but not the minimum. So this one is true. Okay, then let's take a. So here is we are taking about the topology. So we will not discuss this one. So we discuss this one. Which of the following is or are true? This the usual topology admits a metric which is complete. Okay, again this is because this is topology, so we are not connected. This is your connected set. This is not also related to this one. Here is the Hausdorff connectedness, so I will not consider this one. So we can take this we can take D1, D2 are matrices on Rn which are defined as this one, and this is the usual metric. Then decide which of the following is a metric on X. Okay. So here is this is the metric on X. The difference is not a metric on X. The sum of the metric is on. If you multiply by any number, then it is a metric, and the sum is a metric. So this is a metric. So the only thing is that the difference is not metric. So this is not true. The rest of the things are true. So here is path connected. I will not consider this one. Okay, so let us take here is yes. So here you can take XB. Then arbitrary open set G is countable union of closed sets. Yes, this we have proved. Any open set is the countable union of closed sets. This we have proved. So it is true. Now arbitrary open set, okay, cannot be countable union of closed sets if X is connected. No, this is not true. Arbitrary open set in X is a countable union of closed sets only if X is countable. No, this is also not true. Arbitrary open set in X is a countable union of closed sets only if X is locally compact. No, only the first is true. Any arbitrary open set in X is a countable union of closed sets. So this you can prove. And now here is also connectedness. So I will not go to this one. So I stop over here. So these were some exercises which were appeared in the NET exams, and they are all related with the metric spaces, or you can say the topology. But here is the only thing is that we have not discuss about the connected net. So some are not in your you can say in your course. So that you can see in the course of a topology. So thank you very much.